Welcome APChem students to another edition of Advanced Kentucky APChem TV. I want to get right into talking about mechanisms and rate laws to maybe give you some idea of what you might expect on the APChem exam. So if you have any questions, make sure you tweet them in to asklewky.com or something like that. Reaction rates deal with how quickly reactions occur, and you're likely to see questions on the APChem exam about that. It's also a window into how reactions occur, not just how quickly reactions occur. And the first thing we want to know is, what do we mean by a reaction rate? So by the reaction rate, we mean the change in the concentration of some species in the reactant, whether it is the product or the reactants, over time. So if you can imagine, we have some container and we put some reactant in it, let's say that's reactant A, and we have some other reactant, which will be these blue dots, which you may or may not see, which we'll call reactant B, and we have some chemical equation that says, for example, 2A plus B goes to 2C. What will happen is that the stoichiometry of the reaction is fairly straightforward and non-negotiable. Every time 2A particles and a B particle get consumed, they will become 2 particles of C. And that will happen until, assuming this is an irreversible reaction and we're not dealing with an equilibrium situation, that will happen until we run out of our limiting reactant. The reaction rate tells us how quickly this happens per unit time. So the definition of the reaction rate will be the change in the concentration of some reactant, I'll just call it R, over the elapsed time. And one little technicality we've got to throw in here, because in this instance, the stoichiometry is such that I'm going to use 2 particles of A for every particle of B. I really should, if I'm using reactant A, divide this by 2, whereas if I'm using reactant B, it will be used up at half the rate of reaction C. And I'll just put an N there to represent the stoichiometric coefficients. And obviously, reactants get consumed and products are formed in a reaction. So this is really our definition of the reaction rate. And some reactions, you know, happen very quickly, some happen on a glacial pace. When we talk about the rate law, we're telling us, what does this reaction rate depend on? And typically, it will depend on the concentrations of our reactants. So in this case, the concentration of A and the concentration of B, and some constant, which we call a rate constant, usually signified by a lowercase k. And there are going to be some powers up here, some exponents. And I'm going to write lowercase a and lowercase b for those exponents. These exponents are the orders of the reaction with respect to each of these reactants. And they're typically 0 or 1 or 2. They're usually integers, although in rare instances they can be rational numbers like a half, and even negative numbers. But we're not going to worry too much about that. It's important to emphasize that these orders do not necessarily match the coefficients of the rate law. This is a little bit different than you might study in equilibrium, where the coefficients of the equilibrium expression are necessarily the coefficients of the balanced equation. But in kinetics, that's not necessarily true, and it's important to see why that's not necessarily true. And that's why reaction rate laws give us some insight into a mechanism. So by a mechanism, we really mean a detailed picture of how an overall reaction occurs. It would make sense if we've got a reaction in a gas or solution phase to think that these particles react when they collide, and not just collide, but there are conditions a collision is a necessary but not a sufficient condition. They've got to collide with enough energy to rupture the bonds that had been there, and with an acceptable orientation. Well, if you've got a sample of a gas or a mixture of gases, two particles are going to be colliding all the time. The frequency with which three or more particles collide will be negligible. And think about, kind of macabre illustration. If you've got a 6 or 7 car pileup on the freeway, well, those 6 cars didn't all collide at the same time. You had 2 cars collide, and then a third car plowed into it, and someone else was texting and hit them. So fortunately, no one was injured, so it's okay. But our fundamental principle for AP chemistry is that even when the reaction equation involves many, many particles, 3 or more, there is a series of bimolecular, 2-particle, or unimolecular, 1-particle steps that will generate that overall equation. So in the case of, let's say we have 2A plus B going to 2C, and this is all happening in the gas phase. Well, my reaction equation shows 3 particles, but they're probably not reacting, colliding all at the same time. So we might imagine that an A plus a B might generate some intermediate, let me call it M. And then this might be step 1. And then in the second subsequent step, that M will react with another A to form 2C. So if this is our slow step, and this is our fast step, then the rate of the overall reaction will depend on the rate of the slow step. And since this involves 1 particle of A and 1 particle of B, we would expect that the rate law would tell me that the reaction rate equals K times the concentration of A to the first power times the concentration of B also to the first power. So the rate law is going to reflect the stoichiometry, not of the overall reaction, but of that rate determining step. And if you have the notes in front of you, you would know that the rate determining step is often, but not always, the first step. And we'll see some examples of that. So this is the relationship between the reaction mechanism and the rate law. Now, how would you find the rate law if you don't know the reaction mechanism? Well, you would have to do some experiments, and hopefully some of you have done some of these experiments, but you would need to be able to measure the reaction rates under conditions where you know the concentrations of all of our reactants, and for example, and then you will do several trials where you might change the concentrations of the reactants and measure the effect on the reaction rate. So in our scientific vocabulary, we would say that the independent variable would be the concentration of our reactants, and the dependent variable would be the reaction rate. If, for example, we find that doubling the concentration of A with no change in other factors, and that might include the concentration of B and the temperature, which is kind of related, hidden in that value of that rate constant K. So let's say a doubling of the concentration of A might lead to a doubling of the reaction rate. That would tell us that this exponent here would be 1. If doubling the concentration of A led to a quadrupling of the reaction rate, then since 4 equals 2 to the A power would be solid, and I'd say A equals 2, that would tell me it's second order. Or it might be that a doubling of the concentration of A would cause no change in the reaction rate, and that would tell me the reaction rate is independent of the concentration of A. Even though A is involved in the overall reaction, it would not be involved in the rate determining step, and then this might be a 0. And you can do the same for B. So it's important to understand that the rate law reflects the mechanism of the rate determining step, and that the value of K will include information about what the temperature, the geometric considerations, the frequency of collisions, but it's also going to have units that are appropriate to the rate law. So our reaction rate will always be expressed in units of concentration change versus time, typically molar per second or per minute. Although with gas phase reactions, it's possible that you might see this as a change in pressure. But if this will be a change in, have units of molar per second, then the units of K will always have units of time in the denominator, and it will be molar to the 1 minus A plus B, where these are the orders with respect to the reaction. And those are the fundamental principles. I want to go over some problems that you might have if you looked at the video or the problem set I sent out with this. And I'll just kind of read them off to you and go over some of them. So the first question says that in the gas phase, nitrogen monoxide reacts exothermically with oxygen to form nitrogen dioxide according to the balanced equation that is given. And I will take a moment. So if you're watching this on video, I'm going to go over these questions. I would encourage you to pause the video and try to answer the questions yourself before you go over my responses to them. So the balanced equation for the reaction of nitrogen monoxide in the gas phase is 2NO would react with O2 to form 2NO2. Part A of this question tells us that under a certain set of concentrations and temperature, the concentration of oxygen is decreasing at a rate of 0.020 moles per liter per second. So I'm going to make a little column here that the change in the concentration of oxygen is decreasing. That's a minus sign, 0.020 molar per second. And you're asked for the rate of change of each of the other species at this particular instant. And this looks like a kinetics question, but it's really not. It's a stoichiometry question. Because what I need to understand is that this balanced equation tells me that I use up 2 of these nitrogen monoxide molecules for every 1 oxygen molecule, and I form 2 of those. So the rates have got to be in that same ratio, and I can pretty clearly multiply this by 2/1 to tell me that at that instant, the concentration of nitrogen monoxide is going to be decreasing at a rate of 0.040 molar per second. And the rate of change of the concentration of NO2 is going to be positive 0.040 molar per second. Really stoichiometry. Part B then goes on to ask why it's unlikely that this reaction would occur in a single elementary step. And I think you would be expected to say, well, let me look at my equation. It involves more than 2 reacting particles. In fact, it involves 3 reacting particles. And the chances of 3 particles colliding at the same time and place are negligible. So this reaction would have an underlying mechanism which would occur in a series of bimolecular steps. So what is that mechanism? Well, we go on to say that the reaction mechanism does occur in 2 steps, and step 1 involves the collision of 1 nitrogen monoxide molecule with an O2 molecule, and I'll stop writing gas phase since these are all in the gas phase, to form NO2 plus O. And this is a pretty special particle. That's an oxygen atom, something you would not normally expect to find. It's not very stable. It doesn't satisfy the octet rule. Very high energy, but it's still exists as an intermediate. And notice that this step, like all the steps in a reaction mechanism, is itself balanced. I've got 1 nitrogen atom and 3 oxygen atoms on both sides, but it does reflect a change. In step 2, a second NO will react with that oxygen atom to form another NO2. And Notice that I can combine these two steps to get the overall reaction. This oxygen, this atomic oxygen, which is produced in an early step and then used back up almost immediately, since this is going to be our fast step, is called a reactive intermediate, or just an intermediate. And that disappears, and I'm left with two nitrogen monoxide molecules reacting with one oxygen molecule to form two NO2 molecules. If this were the mechanism, well, the question here says, asks you to identify the intermediate species in the reaction mechanism, and that would be the thing that is made in an early step and then used up again, so it never appears in the overall equation. It asks us to write the rate law for the overall reaction, and to get the rate law, we would look at the slow or the rate determining step, and we would have to write that the reaction rate equals some constant times the concentration of NO to the first power times the concentration of O2 also to the first power. Obviously, you don't have to write the exponent as 1 if you don't want to. I like to emphasize that. But it's going to be first order in both nitrogen monoxide and oxygen. And then you're asked for the units of K. We can't really do anything about a numerical value because the problem doesn't give us reaction rates or concentrations, but we do know the units of K are going to be consistent with the rate law, since the reaction rate will be in molar per second, and each of these concentrations will be in molar to the first power. The units of K can be written as molar per second divided by molar squared, or kind of funny units of 1 over molar second. Sometimes you'll see that written as molar to the -1 times second to the -1. Kind of a funny looking unit, but it's what it is. And will reflect any time we've got an overall second order reaction, those will be the units of K. So let's say this reaction occurs at a fixed rate, in a fixed volume, and a constant temperature. What would happen to the value of the rate constant? And the value of the rate constant, because it's constant for a particular reaction at a particular temperature, wouldn't change. Hence rate constant. Sometimes the vocabulary does make sense. But the reaction rate would decrease over time because these concentrations of my reactants would decrease. So as we start out, usually with high concentrations of reactants, the reaction rate will be going pretty quickly. Since this is not going to change, as my reactant concentrations are depleted, the reaction rate decreases. So when we start graphing these, typically if we were to graph the concentration of NO versus time, we would start at some value, and we don't usually see a straight line. The straight line would be indicative of a constant reaction rate. Usually we see some sort of curve that is decreasing but with a curving upward. So if those of you who are in calculus would talk about negative first derivatives but positive second derivatives. Don't worry about that. All right. Oh, the problem goes on. It asks us to select a reaction profile that is consistent with that mechanism for the reaction, and we've got this two-step mechanism, and each step will typically have its own activation energy. So you're given a couple of choices here. A reaction profile is a graph of energy versus time, where we have reactants and products. Now, since you were told that this is an exothermic reaction, the products are going to be at a lower energy than the reactants, and that's going to eliminate two of the choices on your question sheet. In fact, this difference here is just going to be the delta H of the reaction. So it's an exothermic reaction and delta H is less than 0. Since we've got a two-step reaction mechanism, with the first step, the slow step, we would expect to have two humps with a larger activation energy for the first one. So you should see something like that, where this represents the activation energy for the slow step. And once that's happened, it's kind of like a roller coaster. Once you get over that first hill, well, the following hills are pretty quick. And then we throw in one more question to say that what might happen, or how could we ever see a rate law that is more than second order? And it happens. This is a little bit less common, but still is a favorite question on the AP Chem exam. Let's say that we change the temperature for this system. And then often when you change the temperature, you might have different intermediates or a different reaction mechanism, and therefore a different rate law. And yes, some of you are thinking, well, what if you're just at that in-between temperature? Then things get pretty complicated, because you might have the reaction going by several different mechanisms, at least two. But we're not going to worry about that. Let's say we have now a new mechanism where step one is a fast equilibrium. And that where two NO molecules might exist in equilibrium with an N2O2 molecule, and that's going to be pretty fast. And step two, which is going to be our slow step, is going to involve the reaction of N2O2, dinitrogen dioxide, with an oxygen molecule to form 2NO2. And this is certainly a plausible mechanism for this reaction. If we were to ask now for the rate law, we would look at the slow step, and I think we said that step two would be the slow step, and write that the reaction rate is K times the concentration of N2O2 to the first power times the concentration of O2 also to the first power. And while that would certainly be accurate, rate laws can't involve intermediates, or they don't conventionally involve intermediates. And N2O2 is certainly an intermediate, since it shows up in the first step but is used up in the second step, and it doesn't show up in the overall equation. So we've got to figure out some way of getting rid of that species from the reaction, from the rate law. And the trick here is to use what you know about equilibrium and to look at this first chemical equation, and from that say that, well, I know if that's an equilibrium, there is an equilibrium constant expression, which will be the concentration of N2O2 to the first power over the concentration of NO squared. And from that, I can rewrite the concentration of N2O2 as some KEQ times the concentration of NO squared. And now I can plug this expression into what I had written as the rate law, and that gives me reaction rate equals K times the big equilibrium constant times the concentration of NO squared times the concentration of O2. And obviously I've got a constant times another constant, so I would usually just combine those into a different constant, call it K prime, times the concentration of NO squared times the concentration of O2. And yes, if I look at this, it happens to coincidentally match the coefficients of the overall equation, but that's really kind of coincidental. There's a fairly intricate and nice reaction mechanism involved there. So I hope you did well on that problem. Feel free to tweet me at asklewky.com, or not. I don't think you need the .com. Let's look at the second question here. And this involves another reaction of chlorine dioxide reacting with fluorine. So our overall equation is ClO2 plus F2, and I need two of those, and they form ClO2F. And two of those. You always got to start with a balanced equation. you're given a set of data, and I'm going to go ahead and try to copy this. So these are going to be different trials. Trial 1, 2, 3, 4. So my initial concentration of chlorine dioxide is 0.040, and these are all in molar, 0.1. And I don't care about the concentration of this. These are initially, so these are all initial concentrations, right? When I've set up my reaction, and it's just getting started, so I typically don't have any product. I can measure the reaction rate, or the rate at which the fluorine is consumed, and in this case I get a value of negative 2.4 times 10 to the negative third molar per second. And that really doesn't tell us anything yet. If I have a second trial where my chlorine dioxide concentration is 0.08, but my fluorine concentration hasn't changed, and I measure that the rate of consumption of the fluorine is 4.8 moles per liter per second. Now I'm getting somewhere. I've got some information I can do something with. I'll go ahead and copy all the data here. So 0.040, 0.4, negative 9.6 times 10 to the negative third, and 0.16, don't know that, and negative 4.8 times 10 to the negative third molar per second. So there are a few questions, some of which have to do with kinetics, some of which are going to be really more stoichiometry or general chemistry questions. You're given, for this problem, a graph that shows how the concentration of chlorine dioxide changes over time during the reaction. So we've got concentrations over here, and time over here. And it doesn't tell us what that time is, but this goes here. And the chlorine dioxide starts at here at 0.04 and decreases with kind of that decreasing but curving upward that is very typical here. You're asked to get the concentration, and this reflects the data from trial 1. You're asked to sketch what happens for the concentrations of fluorine and the product ClO2F, and you should know from the stoichiometry that the fluorine is going to start up here at 0.1 moles per liter, and its decrease will be half as great as that of ClO2, because it's a 1 to 2 mole ratio. So it's going to, instead of decreasing by 0.04 moles per liter, it will decrease by 0.02 moles per liter, 0.08, and look something like that. As if I were to take this graph and kind of scrunch it down halfway and move it up to here. That would be a scaling and a translation for those of you who don't like the scrunch word. What would happen to the concentration of chlorine ClO2F? Well, it would start out at 0, and since it would be formed in the same ratio as ClO2 is consumed, it would come up and do something like that, finishing here at 0.04. And that really has nothing to do with kinetics. That's fundamental stoichiometry. But understand what we're showing in this, and we'll have another video a little later that will talk about where these curves might come from. This is typical data that you might get and has to derive the rate law, and there are some complicated math ways to do it, not really all that complicated, but I think if you have a really good understanding of chemistry and what these orders mean, you will see that if I compare now trials 1 and 2, I've doubled the concentration of ClO2. I have no change in the concentration of fluorine, and my rate of consumption, my reaction rate, is also doubled. So this generates the mathematical equation that 2 to the A equals 2. And clearly A here has got to be 1, which tells me that the reaction is first order in ClO2. If I want to know now what is the order with respect to fluorine, I've got to get two different trials, and I can now use the fact that conveniently trial 1 and trial 3 have no change in the concentration of ClO2, but I have a quadrupling of the initial fluorine concentration, and a quadrupling of the rate. We don't have to do everything with doublings. So now I generate the equation that 4 to the B equals 4, and pretty clearly that B also has to be 1. So this gives me the overall rate law, and the APChem readers are usually pretty good sticklers about this. If they ask for the orders, you can say A is 1 or B is 1, but if you're asked for the rate law, you need to write the entire equation, that reaction rate equals some constant times the concentration of ClO2 times the concentration of F2. So this is the rate law, and sometimes students who abbreviate it or just leave out the K, which is wrong, or even just leave out this part, which is arguably okay. It's they may not get credit for that. So make sure you answer the questions that are asked, please. Once you have this as the rate law, you can find the value of the rate constant K, and here we actually do have some data. So you should be able to use data from any one of these 3 trials to plug into this rate law, and you should get the same value of K, at least if you've done the math correctly. So I'm going to go ahead and use the values from trial 1, where the reaction rate is 2.4 times 10 to the negative third molar per second equals K times the concentration of chlorine dioxide, 0.040 molar given to us, times 0.1 molar. And when you go ahead and solve for K, you would get 0.6. And the units there, again, this is an overall second order reaction, so it would be molar to the negative 1 seconds to the negative 1. Part D is very similar to the question we did earlier. We're looking for the change in the concentration, the initial changes, rates of change of ClO2 and ClO2F for trial 1, and because of the 2-to-1 stoichiometry here, the rate of change of ClO2 would be twice that, or negative 4.8 times 10 to the negative 3 moles per liter, and the rate of change of ClO2F would be positive 4.8 times 10 to the negative 3 moles per liter. We were missing this number, and the part E asks you to calculate that initial concentration. And now it's really just a question of substituting in what you know if you have a rate law, and now we now have a value of K and the reaction rate, so we would write here that 4.8 times 10 to the negative third molar per second, which is the reaction rate, would equal 0.6 per molar per second times 0.160 molar times the concentration of F2, and go ahead and solve that, and I think you can all do that to get 0.050, and the unit there should be molar. It's incorrect in my notes here, so I'll go ahead and change that. I've got the wrong unit there. I've got molar to the negative 1, but it really should be molar. Again, then they're asked for whether this mechanism is consistent with, or a mechanism is consistent with that rate law. So I'm going to change that and say, if this is our rate law, can we think of a proposed mechanism that might be consistent with that? And it shouldn't be that hard, because we would have a slow step now that would involve one of those particles and one of those particles. So our slow step might be ClO2 reacting with F2 to form something, and that something might be, well, there are different ways to do this, but since I know I'm going to want to form 2 of those, let me get one of them out of the way and just form one product molecule, and that would leave me with a fluorine atom. And then in that second step, the fast step, I would take that fluorine atom and react it with another ClO2 to form another ClO2F, and there's my intermediate. Is that the only possible rate law consistent with that mechanism? Well, no. I could certainly have some thing here where I don't get a free fluorine atom, but rather I get ClO2F2, and ClO2F2 would react with another ClO2 to form two ClO2Fs. I couldn't really decide on the basis of that which would be correct. And finally, a nice quick question here that has environmental implications. Ozone, many of you may know as something that is dangerous on the surface of Earth, but it's an essential component of the upper atmosphere. It does a good job shielding us from harmful ultraviolet and X-rays from the sun. And if you were of a certain generation, like mine, you would have been concerned several years ago that the ozone layer, there's a hole in it. And it turned out that the ozone was being degraded by the propellants that aerosol cans used to use. That's been phased out since in an international treaty called the Montreal Protocol. But the mechanism by which it was being used up was the following. So an ozone molecule happily absorbing harmful sun rays in the upper atmosphere would react with a chlorine atom. And that chlorine atom, that's not Cl2, that's atomic chlorine, so it doesn't exist, it's not very stable, but it would form an O2 molecule plus OCl. And that OCl, and that's our slow step, in a subsequent fast step, OCl reacts with another ozone molecule to form two O2s and a Cl. So this is a little bit different. We certainly have an intermediate here. This OCl free radical is produced and then used up, and that would be a reactive intermediate. But we have something here that's a little bit different. We have a chlorine atom that's consumed and then later spit back out. And when that happens, this particle is called a catalyst. Some of you are in AP biology and you'll know all about catalysts, I hope. It's pretty essential for life. But a catalyst is something that is used and spit back out, and therefore its concentration never really changes. It's not consumed in the reaction. It's kind of like a matchmaker, and it facilitates the reaction by providing a mechanism with a lower activation energy. So part A here asks you to identify the catalyst, and chlorine is the catalyst. If we now combine these two steps into the overall reaction mechanism, well, the reactive intermediates cancel, so do the catalysts, and we have 2O3 going to 3O2. And that would be the overall balance equation showing that ozone is being degraded into regular old diatomic oxygen. What's the rate law? Well, again, we look at the slow step, and unlike intermediates, catalysts can appear in the rate law. So that's going to be pretty straightforward, I hope. The rate law here tells us the reaction rate equals some constant times the concentration of O3 to the first power times the concentration of Cl to the first power. And it's perfectly okay to leave that catalyst in there. In fact, you have to leave that catalyst in there. And then in part D, why do we really care about chlorine degrading our ozone layer? Because ozone can also react with carbon monoxide to form oxygen and carbon dioxide. Any carbon monoxide in the upper atmosphere would also get rid of ozone. But we're not so concerned about that because, well, every one carbon monoxide molecule can only react with and use up one ozone molecule, whereas one chlorine atom could use up millions or billions or really an indefinite number of ozone molecules. And we've got to be really careful with catalysts. So that's a little set of problems that you might see like that type on the AP Chem exam on reaction mechanisms and rates and why they're important. Please tweet in those questions to Ask Lew KY and or email me at lacampora@kscc.com, and I look forward to hearing from you, but good luck on the AP Chem exam.